like we have some tardy students today.
You still start on time?
Yeah, they trickle in. Good morning and welcome to the CERIAS Computer Security Seminar from Purdue University. Our speaker today is Professor David Evans from the University of Virginia. His topic is titled, Where's the FEEB? The Effectiveness of Instruction Set Randomization. David?
Okay, well, thank you for inviting me to come visit. I will explain what a FEEB is a little later for those of you who aren't used to reading Intel x86 opcodes backwards. I won't explain what the picture is. If you don't recognize the picture, talk to someone who's at least as old as me, an American, and they can explain that part to you. So it's been observed recently that we're in danger of having a computing monoculture. This was observed most famously by Dan Geer, who got fired for observing it. And the problem with the computing monoculture is if all the computers and all the routers are running the same software, if there's a vulnerability discovered in that software, an attacker can design an exploit that compromises millions or billions of machines at once. And the reason it's billions and not just millions is because cell phones are all running the same software too now. So biology has found a solution to this. And the solution that nature uses for this is to have diversity. There's enough diversity within a species so that one parasite won't kill all members of that species. And nature uses a very expensive mechanism to preserve that diversity. And I don't know about Purdue students, but I know that UVA students spend a lot of effort trying to do their part to maintain diversity in the gene pool. And even beyond that, even it's not just college students that do this, it applies to all organisms on Earth, basically. Because when you reproduce using this rather peculiar mechanism, half of your genes aren't even appearing in the offspring. So right away, you're doubling the cost of propagating your genes. So there must be a really good reason for this. And the only reason biologists have come up with that makes any sense is to preserve diversity. And the reason we need diversity is otherwise a species could be wiped out by a single parasite that evolves to attack that species. So people in the computer security community have noticed this. And there's been a flurry of papers over the last several years where people have proposed different techniques for obtaining diversity in computer systems. What we don't have is any theory that says how well those techniques work. Any way of really understanding whether or not they prevent an attack from being able to take out all systems at once. And I don't have a theory of that yet either. What I do have is some insights into how well one of these particular techniques works. And so the technique I want to talk about is called instruction set randomization. This was introduced simultaneously by two papers in CCS a couple years ago. And the idea is that a large class of attacks depends on an attacker injecting code that runs in a process on the victim's machine. And that injected code, in order to behave like the attacker wants, the attacker needs to know the instruction set of the machine it's attacking. So if you can change that instruction set and hide it from the attacker, then the attack won't work. Unfortunately, it's pretty difficult to design new instruction sets. This requires a lot of effort, and building a new microprocessor is very expensive. So we need some way of getting this property without needing to do that. And the way to do that is to use a randomizer. So instead of running the executable directly, we have a program that takes the executable, takes the secret key, and produces a randomized executable. And then when we execute the program, instead of executing it directly on the processor, we have some de-randomizer that surrounds the processor and will take out the randomization. So it will decrypt the randomized executable to get the original code back, and that's what runs on the processor. So for this to work, the de-randomizer needs to know the secret key as well to be able to undo the randomization that the randomizer did. And what should happen if an attacker finds a way to inject malicious code into a running process is the only way for the malicious code to get to the processor is to also go through that de-randomizer. And if the attacker doesn't know the randomization key, well, that's going to produce effectively random bits. And when you run random instructions, they're not going to do what the malicious attacker wanted. They're probably just going to crash the machine. So this is still an effective denial of service attack, but it doesn't propagate, and it doesn't do any real damage. So in order to actually implement this, we have some design parameters we have to decide. We have to decide what the randomizer does, when it happens, and when the de-randomizer happens. And the two proposed implementations make different decisions here. The Columbia implementation is focused on getting high performance. So they wanted a design that they could implement inexpensively in hardware. The RISE implementation is focused more on security with the software implementation. The randomization function in both cases is just XOR. So you have some secret key, and you're XORing the bits of the instructions with that key before you execute them. The key size for the Columbia machine needed to fit in a register. So it's only 32 bits, and that same XOR key is used for all instructions. For RISE, they could afford a longer key, so it's stored in memory. The key could be as long as the program. And so each location has its own key bits. When you execute an instruction to that location, it's going to be XORed with the key at that location. So any questions on this before I go on to talk about evaluating its security?
I have a question on
Yes.
the program length. Is it just the length of a text segment or the?
It could be the length of the text segment. So every location where there's potentially code can have its own randomization key. There's no randomization going on in the data.
It also will try to randomize the data segment for the.
You could randomize the data as well. The focus has been on hiding the instruction set. So at least for this particular diversity defense, there's no focus on the data. Yes?
And so when we say randomization, do we mean the order of the statements? Do we mean add some, no ops?
So all these systems are doing is XORing the actual bits of the instructions. So there's no reordering, there's no other changes. You could certainly design systems that would do other changes, but their focus has all been on we can hide the instruction set by XORing the instructions and then XORing it out before we execute them. Okay, so we want to understand how secure these are. And certainly, one more question, yeah?
Okay, so I'm assuming the XOR is just used as just a proof of concept and won't actually be used if you were to continue on development. Such as, what if the attacker were to realize that this kind of implementation were in place and they were to derive the key based off of it being exclusive or.
So that's what I'm going to talk about how to do next, right? So these were certainly proposed thinking XOR provides a lot of security, and it does, right? It prevents all existing attacks that depend on executing instructions on this processor, right? And if you can protect that key, then it's gonna work fine, right? Now, you're right to notice that XOR is not a very secure encryption algorithm, right? If someone can obtain one plain text ciphertext pair, then they know what the XOR key is. So that's exactly what our attack attempts to do. Okay, so how secure are these systems? And our answer is, well, they're not very secure. And it slows down an attack by about 5 minutes. And that depends on certain circumstances being true. The motivation behind this work came from a paper that looked at another diversity defense, which was memory address space randomization. And they were able to attack that using a brute force attack to find the key. And the key space was only 24 bits. So a brute force attack works pretty well against a 24-bit key space. ISR, that's not going to work. The key space is much larger. With the Columbia implementation, it's 32 bits. With the RISE implementation, it's arbitrarily long. So we can't do a brute force search on the whole key space. What we need to do is find a way to attack it in fragments. And in order to attack it in fragments, that means we need some way to tell if a partial guess is correct. So here's the basic idea. Right? We have a remote attacker. We have an ISR protected server. The remote client sends a packet or sequence of packets to the server. This is the guess. If the guess is incorrect, those bits turn into basically random instructions and the server should crash. If the guess is correct, the server should do something that the remote attacker can observe, and the attacker learns those bits of the key. Okay, so in order for this type of attack to work, we need some properties of the server. We definitely need a vulnerability. We need some way of injecting our guess into the server. Luckily, most servers are vulnerable, so this isn't too much of a problem. Any old buffer overflow will do. If we didn't have vulnerabilities in servers, we wouldn't have to worry about any of these techniques at all. Since we need to make lots of guesses, we also need some way of making repeated guesses without the randomization key changing. So that means we can crash the server without the server being re-randomized. So some implementations would re-randomize the server every time you load it. As long as the server forks processes, we can still do this. So if it forks on request like Apache does, we can crash one of those fork processes, but the other children and the parent are still running with the same key. So the third property we need is it has to be observable. We need to be able to observe as a remote attacker whether or not we crash the server. And the final property is it needs to be easy to cryptanalyze the key that's used for the randomization. We're doing all this work to learn one plaintext ciphertext pair. That has to be enough for us to figure out the key, because if we want to inject code into the process, we need to know what the key is. Luckily, with XOR, this is really easy. OK, so we need to have some idea of a short chunk of code we can put in the process and tell whether that guess is correct. The shortest thing we could do is a 1-byte instruction. And we probably need a control instruction. Otherwise, we can't tell what's going on. But if we inject a return instruction, well, if the guess is correct, the process returns. And that should be noticeable. If the guess is incorrect, the process should crash. The problem with the return attack is even if the guess is correct, the process is likely to crash soon anyway, because it leaves the stack in an inconsistent state. So this only works on vulnerabilities where the server does something that we can observe remotely before it crashes. So what I'm going to focus on today is the jump attack, which works on almost all vulnerabilities. So the jump attack is to try to guess this FEEB instruction, which is a jump with offset -2. When we put that on the stack the right way, it looks like FEEB backwards. And that means we need to guess 2 bytes at once. So there are 2 to the 16 possible guesses, which seems reasonable to brute force. And we'll notice if we're correct, because when we jump to offset -2, we're jumping back to the same instruction we just executed. So that means it's going to produce an infinite loop. The socket's going to stay open. So when the server crashes because the guess is wrong, the socket gets closed. The remote attacker can notice that. When we have the infinite loop, the socket stays open, and we can tell that we guessed correctly. OK, so here's what this looks like. So we've got a vulnerable buffer on the stack. We've overridden return address to jump to some location. And we've tried to guess at that location the jump -2 instruction. If we guess correctly, we get an infinite loop. So once we've found one correct guess, right, we need more bytes because each byte has its own encryption key. Well, we can move up to the next byte. And if we move up 1 byte at a time to guess the next one, well, we can do that at 1 byte at a time. So we only need up to 256 attempts. Right, we can use the ones we've already guessed to put known things there. So we can put the -2 offset in the right place and guess the remaining bytes much more quickly. OK, so there are 4 things that might happen. Right? This is a simple case where if we always guess correctly, we get the infinite loop and we observe that. And if we guess incorrectly, the server crashes. It'd be great if that was true. Right? We know right away when we have the right guess. Unfortunately, it's not that simple. We can guess something that's incorrect, and the server goes into an infinite loop anyway. That would be a false positive. We could guess something that's correct, and the server crashes anyway. This shouldn't happen too often. Right? This would only happen if there's something else that causes the server to crash that time. So we don't have to worry about that case. And we could guess something that's incorrect and causes the server to crash, and we observe that, and we make progress because we know that's not correct. The case we have to worry about is this false positive case, where we guess something that's not correct, but the server behaves like we made a correct guess, that it goes into what looks like an infinite loop anyway. So there are lots of things that could cause this. Right? If we did, instead of guessing a jump -2, the bytes we happen to inject decrypted to jump -4, and whatever instruction happened to be at the -4 location was a harmless 2-byte instruction, then we would still get an infinite loop. but we wouldn't know the correct mask. We could also guess something like a jump non-zero, and if the state of the processor is such that that condition would be satisfied, then that would behave just like an infinite loop as well. So the other kinds of things that could cause the behavior to look like an infinite loop, even though we didn't guess correctly, well, we could just guess something that's harmless. And by harmless, I mean any guess that doesn't cause the processor to crash right away. We could change the state of the processor, but it doesn't cause it to crash. And then some subsequently executed instruction could produce an infinite loop. The third case is probably not too serious. We could make the incorrect guess, and it could cause the server to crash. But because of network lag or because of load on the server, it doesn't crash quickly enough. And then the client of the attacker would think, well, it's an infinite loop. You have some amount of time you can wait to decide if it's an infinite loop or not. And if you exceed that time, even though the server crashed, but you didn't crash in time, then you would infer that's an incorrect guess as well. We can sort of solve this problem by just increasing the timeout that we're willing to wait. That slows down the attack, though. OK. So the good news is we can distinguish those cases. Right? So if we have multiple guesses at some location that all produce infinite loops, we can try injecting different instructions there. And guessing the different masks that produced an infinite loop before, we encrypt some other instruction with that mask, and we see what we get. And if we put the no-op in, if the mask is correct, that will do nothing, and it will go on to the next instruction, which produces the infinite loop, because we can put our known infinite loop instructions there. So this will allow us to distinguish some of the incorrect guesses. It doesn't always work. So there's a difficulty that the instruction set is very dense. And if two of the guesses differ in only 1 bit, there's no harmless instruction that is always harmless for changing 1 bit and always harmful if we have the other version of that bit. So we can't always distinguish here. But with enough different harmless instructions and some other tricks, we can distinguish them. Turns out that there's actually even better news about the false positives. What causes them is not random. Right? The false positives are caused because of the structure of the instruction set. So we know that when we've hit a false positive, we're running into one of these things that can cause it, which is most likely a conditional loop. And the instruction set very conveniently organizes where the conditional jump instructions are, that they all start with the same 4 bits. So all the opcodes that start with 7 are conditional jumps. And they come in complementary pairs. And what that means is if the last bit is a 0 and the jump would not be taken, then the complementary instruction with the last bit of a 1 would always be taken. So you can think of one of these would be jump if 0, one of them is jump if non-0. And all 16 of the conditional jump instructions have this property. That if we flip the last bit, one of those 2 is guaranteed to be taken. So this means with just 32 guesses, we can always find at least one infinite loop. Because all we have to do is guess all possible values for the first 4 bits to try to find the 7, and guess both possible values for the last bit. And so we only need to try 5 different bits. The other 3 bits can be anything. We don't care what they are. We don't need to make guesses there. So we only need 32 guesses to find an infinite loop. Once we find one, we don't know which one we found. So we need some extra guesses to distinguish which mask is actually at that location. And that requires about 8 additional guesses. So here's what this looks like now. So once we've learned a few locations the hard way, what we can do is place a near jump there with the offset, which is the original return location. So this has a nice property that we're not creating any more infinite loops. Right? And infinite loops are a problem. If we create too many, the load on the server gets so high that we can't tell when we crash it or not, because it takes so long to respond to requests. But by doing this, we don't need to produce any more infinite loops. We fill up the buffer that we've already guessed up till the one we're guessing with these CD instructions. And what a CD is an interrupt. And when the parameter in an interrupt is CD, that's guaranteed to crash a user process, because user processes aren't allowed to run the interrupt instruction with that parameter. So no matter where we fall in that zone, we're guaranteed to cause a crash. And then for the position that we're guessing, we try to guess a near jump. We try to guess the short jump that jumps to the location where we put the near jump that will continue normal execution. So if we guess correctly with this setup, the program will continue executing normally. We'll be able to observe that remotely. If we guess incorrectly, it's guaranteed to crash. Okay? And the number of guesses we need is really low. Right? We need, on average, 15.5 expected guesses to find the first infinite loop. And then we need, on average, 8 guesses after that to figure out what the correct mask is. So we need less than 24 guesses per byte to find the instruction key. OK, so we did some experiments with this using the RISE implementation of ISR that was kindly provided by Stephanie Forrest and her student. The first thing we discovered was that memory space randomization actually works. That we were running these experiments on a Fedora machine. And Fedora, by default, does do memory address randomization. So this meant we couldn't find the stack to inject the attack. We could use the Dan Bonnet's group attack to break the memory address randomization. In this case, it was easier to just turn it off since we control both machines. But the combined effect of the two certainly is stronger than just having one. The next thing we needed to do involved one of the other requirements not actually being true for RISE. So one of the requirements for the attack is that we can run the attack lots of times, cause the process to crash without the randomization key changing. And the way RISE does randomization is it has a cache of the randomization keys for each location. And that cache gets filled up as different segments of memory are loaded. And the problem is when you fork a process, if the keys for that location haven't been used yet, so they'll share the keys for the locations that were already touched, but they won't share the keys after that. So if the place where you're injecting the code is a location that wasn't read before the process forked, then the key there might be different from the key that another process has, another child has. So we modified RISE to avoid that complexity. And that meant that we read the whole cache of key bytes before the process is forked. And other proposed ISR implementations don't work that way. It's certainly a sign that this would be a useful thing to actually build into an ISR design to make sure that every time a process forks, it has its own keys. If you're doing the randomization at compile time, like the proposed Columbia implementation does, you wouldn't be able to do this. All the processes would have the same key. And we find that we're able to obtain the correct key almost all the time. The reason we can't always obtain the correct key is that sometimes the guesses that we want to make to distinguish between possibly correct guesses would require us to put a null on the stack. And because we're doing the attack by injecting bytes on the stack, we can't inject a null, because that would end the string where we're attacking. We couldn't have anything beyond that. So we're not able to make the guess that we want to make, and we're left with more than one possible key at some location. But most of the time, we don't run into that situation. So here's the number of attempts that are required to obtain keys of different sizes. I'll note that this is a log scale, so we're obtaining large keys. To obtain the first 2 bytes takes a little over 4,000 attempts. This makes sense. We need 2 to the 12 attempts to try all the guesses, and we need some additional attempts to distinguish possibly correct guesses. So that's why it's a little above 2 to the 12. And to get 4,096 bytes takes a bit over 100,000 attempts. So the attempts per key starts to decrease. Right? So as we learn more information, we can start using the more efficient attack. We need a lot of attempts to get the first 2 bytes. And once we're getting long keys, it's down to less than 24 attempts per byte. Yes?
It seems that return instruction will be more effective with saying the trap, based on the figure.
Yeah, OK. So the return attack, we're guessing a 1-byte instruction. So let me go back 1 slide. So we can see with the return attack, we can get 1 key byte at a time. We can get the first key byte with just 256 maximum guesses. So it is much faster. The problem is we can't always use the return attack, because it only works on vulnerabilities where the server does something noticeable quickly after the vulnerability. Otherwise, the process is going to crash. But if we are lucky enough, or the attacker's lucky enough, to find a vulnerability like that, then the attack works much more quickly. Thank you for pointing that out. OK. So what really matters to the attacker is not the number of attempts, but how long it takes. And so the time it takes is on this graph, and we're able to get the 4-byte key in just under 3.5 minutes, and getting 4,096 bytes in 48 minutes. So does that seem good enough? How would we decide if that's good enough? So do we know how many bytes we need? Well, we know if the key is repeated, if we get the whole key, we've got enough. But if the key is not repeated, we need to figure out how many bytes we need. So that depends on what we want to inject. And if we just want to compromise one server, then we just need to break enough key bytes to inject the malicious code. And malicious code can be pretty small. The Sapphire worm was only 376 bytes. So we can do a lot of damage with a few key bytes. But if ISR is successful, then we won't just be attacking one machine. We'll be attacking a network of machines that are all protected with ISR. So that means not only do we have to have the malicious payload, we have to have all the code that we use to do the key breaking. And that's pretty complicated, right? It has to manage all this guessing, has to keep track of things. The implementation we have is 34,000 bytes long. I assume if someone worked really hard, they could get that down to maybe 1/4 the size, but not a lot smaller than that. And so to get enough key bytes to hold that code, well, we need to crash the server almost 1,000,000 times. Most sysadmins should notice when their server processes crash 1,000,000 times. So this is probably not good enough. We need to think of some way to make it better. And the way to make it better is maybe to think of, well, we can, instead of being really clever and making the code smaller, we can find a way to inject code without needing to break all the key bytes. So if we're able to break enough key bytes to inject a virtual machine, well, then we don't need to break any more. We can run our attack code within the VM. So VMs are pretty big, right? VMware is 3.5 megabytes. We're not going to inject enough bytes to hold that. There are smaller VMs. Java is a bit over 100,000 bytes, but still bigger than our attack code. At least in theory, we've seen real small examples of universal machines. Minsky designed a Turing machine that only needed 7 states and 4 colors. But even injecting that would require several thousand bytes probably. And it would be hard to write malicious programs that run on it. So we can do better than that, though, because we don't need to build a complete standalone virtual machine. We can take advantage of what the Intel x86 processor already gives us. And it turns out that we can write a micro VM big enough, powerful enough to run any worm that we want with just 100 bytes of code. So I'll show you that code. There it is, just 100 bytes. And it's actually only 76 bytes of code and 26 bytes of no ops. So I won't leave this up long enough for you to actually read it all, other than to get across the point that it is really small. Right? The entire VM fits on this one slide with reasonable size fonts. And here's what it does. So the goal is to be able to run the attack code in locations where we know the key. So we need to have some location where we can take a block of attack code and execute it with known key bytes. And that's what the 22-byte worm execution buffer is. The reason it's 22 bytes is I wanted it to round up to a nice round number like 100 bytes. Right? It could be smaller than that, and the attack would be a little quicker, but the worm would run slower. It could be bigger than that, and the worm would run a little faster. So what we need is a micro VM that will take chunks of code from the worm, copy them into this location, let them run, and then get the next chunk from the worm. So that's what the micro VM does. We have the worm IP address, or the worm instruction pointer, which we initialize to 0, which is the beginning of the worm. Then we copy the worm code into the buffer, and we update the worm IP to point to the next block of the worm. So before we start executing the worm code, we're setting the instruction pointer to point to what should execute next. And then we copy, we save the micro VM registers. So when we get back to the micro VM, it's going to execute correctly. We load the worm registers that we saved. We fall through, right? We don't even need to jump. We fall through the worm code. We run that. Then we save the worm registers, restore the micro VM registers, and jump back to start reading the next block. Okay, so we only need to break enough keys for that. We need all this other data around, but we don't need to break keys to put it there. We just need space for it. Yes?
Well, sometimes the one code may code the system code, or your micro VM take care of the system code.
Okay, good point. So if we want to do jumps, we got a problem here, right? If we do a jump and we try to jump to an arbitrary address, it's going to be somewhere that we don't know the instruction key. So we need to do something special to make jumps. System calls themselves are actually easier than jumps. System calls we can do normally because they just use registers and they return back to where you were. To make jumps, though, is tough. And we're going to need to make jumps. So within a block, we can do a short relative jump very easily. But if the execution buffer is only 22 bytes, that's not going to be good enough. That we're going to need to have loops that are longer than 22 bytes. And 22 bytes is only enough for 4 or 5 instructions. So if you want to make a jump between blocks, well, we need some way of having that happen within the micro VM. If we constrain it to only have jumps from the end of the block to the beginning of the block, we can do it pretty easily. So the way to do a jump is to change the worm IP. That's the instruction pointer for the worm. So to do a jump, we just need to change the value of the worm IP. That value is stored on the stack. Right? Remember the micro VM, before it starts executing the worm code, it updates the worm IP to point to the next block and puts that on the stack. So that means in order to do a jump within the worm code, what we need to do is change the worm IP value, which is stored on the stack. If we want to execute a conditional jump in the worm code, what we do is instead of executing that jump, we use the opposite condition. And for every conditional jump, there's one with its opposite. And we use the opposite condition to jump over the next instruction. And because this has to be at the end of the block, that means we're jumping back into the micro VM. And so if the jump's not taken, we take the opposite jump, and the worm code will continue to the next block. If it is taken, we execute this move instruction, which stores the target address in the location on the stack that stores the worm IP. So when we go back to the micro VM code, when it tries to read the next block of the worm, it's going to read the one from the target instead of the next block. Okay, so that means we can execute any worm we want with this 100 byte of key that we've acquired. So all we need to do to deploy a worm is learn 100 bytes of key. And we can do that really quickly. Right? That takes, on the experiments we've done, the median time that takes is 311 seconds. So just over 5 minutes, and only a bit over 8,000 attempts. And then we can inject into the compromised machine, we put the micro VM code encrypted with those key bytes. We inject the worm code pre-encrypted. So we know where the worm code is going to run because we know where the worm execution buffer is, and we know the key bytes there. So as part of the deployment, we pre-encrypt all the bytes of the worm to have the right key for the location where they'll run. We need to be a little careful because we can't inject nulls. So if the bytes that we want to inject would be a null, we need to insert a no op. And we can do that. And if we're lucky, we can inject the whole micro VM almost all the time within 100 bytes. If we need more no ops, we might need an extra byte or two. And then as we propagate the worm, we need to keep track of the key bytes, because when we find the next machine to attack, we're going to learn the key bytes on that machine. To send the worm to it, we need to XOR out the keys on this machine because it was pre-encrypted with those, and XOR in the keys on the new machine. Okay, yes?
So an attempt, 8,400 attempts. So a crash is, the number of crashes is going to be of the same order of magnitude.
We're going to need to crash about, 8,400 times. That's a lot, but processes crash pretty frequently without getting noticed by sysadmins. So if your sysadmin is really paying attention, they might notice before the worm succeeds. But given it's only happening within 5 minutes, so unless they have something automatic to shut down their network or to shut down their machine when they've seen a certain number of crashes, they probably still don't have time to react to it.
And just a quick clarification question. Of the 256 possibilities in a byte. How many are legitimate instructions in this in this architecture? I mean, what causes a crash? Is it that it is not an instruction?
So almost the instruction set is very dense. So almost everything could be a legal instruction, but given the state of the processor, it's often not. And in our experience, we find about a little less than half the time is a random guess harmless. So more than half the time, random bits will cause the process to crash. So if it's an instruction that, say, reads memory, that could be valid depending on the memory segment of the process you're running it in. Most of the time, it's going to cause a crash. Other questions now? OK, so if we want to prevent this attack, well, we can think about all the things that were necessary for it to succeed and try to change them. So the first thing was to have a vulnerability. And so that's easy to fix. We should just eliminate all the vulnerabilities, and we don't have that problem. And if we can just convince everyone who writes code to rewrite all their code in a type-safe language, we won't have almost all the kinds of vulnerabilities we care about. Unfortunately, efforts to do that have not yet been very successful. So there are other things that we can prevent, even if we use to prevent this attack, even if the server still has vulnerabilities. One thing it relied on was being able to make repeated guesses with the same key. So if we made sure that every time a process crashes, we re-randomize the program, then this attack wouldn't work. You couldn't incrementally guess the key. This would enable a denial of service attack if it takes a lot of processing to re-randomize the program. We could try to make it harder to observe when the process under attack crashes. This is a little tricky to do, but maybe if we modified the kernel, we could make it so a socket stays open even when the server crashes, at least for some amount of time. The most obvious thing we could do is make it harder to cryptanalyze the results. Right? Instead of just using XOR as the encryption technique, use some strong cipher like AES. There's a big drawback to this, though. It takes a lot of time to do that encryption. So if you need to do this encryption while a process is running, which you need to, that may slow down your server enough that it's not feasible. So those are sort of specific defenses against this specific attack. I think what's probably more worth thinking about is, are there more general defenses? So in general, what this attack relied on was being able to break a secret. So if you want things to be more secure, a better solution is to find some way to avoid secrets. Right? It's hard to keep secrets. We've shown one way a remote attacker can learn a secret from a server based on observing its results. There are lots of other ways if you rely on secrets that it could be broken. Maybe a remote attacker can read locations in memory and find the key. Maybe they know an insider who can tell them what the key is. So what we'd like is some way of, instead of relying on keeping a secret for security, having security that doesn't rely on any secrets. And if we have this, maybe we can get to the point where we can actually prove properties about a system that don't rely on probabilistic arguments. Right? Any security technique that depends on keeping a secret relies on a probabilistic argument about how hard it is to guess that secret. If we can find some way that doesn't rely on a secret, then maybe we can make a solid argument that it's always secure. So here's an idea for how to do that. So we want a secretless structure that provides security using diversity techniques. And the idea is that if we have some way of sending the same input to two variants, so we have an input replicator that takes input, sends that same exact input to two variants on our server, and then we have a monitor that looks at what the variants do, and if they do the same thing, sends the output back to the client. If they do something different, and in particular if we can construct variants so any attack that succeeds on one of the variants is guaranteed to make the other one crash, then the monitor knows something's wrong, recovers the system in some way, and doesn't send output to the attacker. So what do we need to make this work? We need some way of making variants that are disjoint. We need to know that anything that works on variant A is guaranteed to make variant B crash, and anything that works on variant B is guaranteed to make variant A crash. So we could think of various things we could use for this. We could use memory addresses, we could say that all addresses that start with a 0 bit are valid in A and invalid in B, and all addresses that start with a 1 bit are valid in B and invalid in A. And as long as the attack required absolute addressing of memory, we would have a disjoint set of variants there. Now, if the attack could use relative addressing, this would not work. So one example is instruction sets. So the goal is to make the variants disjoint, and we can take all possible instructions. And so here's a set of instructions in x86, and we could take all the possible instructions and say we're going to take half of the instructions and make them valid on variant A. And we're going to take the other half and make those valid on variant B. Now we need the second property, which says anything that's valid on variant A is going to cause variant B to crash, and vice versa. So we're going to take the other instructions and make the way we execute these two variants so that all of those instructions cause them to crash. And if we can achieve this property, then we know that any attack code can't work the same code on both machines. It's not a problem for the server code because we can compile the server in different ways. We can compile it for variant A to use the blue instructions, and we can compile it for variant B to use the green instructions. Well, actually, the cyan instructions that are valid on variant B. Right, so we compile it, produce two different executables, but we know that there's no one fragment of code that could run successfully on both variants. Okay, so actually implementing this poses lots of challenges. We haven't implemented this yet. We're working on this now. There's the engineering questions of how do you actually implement this design. Right? We need to build an input replicator, and that's a single point of failure. Right? That if there's a vulnerability in the input replicator, that can be exploited directly. It's not going to the two variants yet. But maybe the input replicator is simple enough we can implement it in hardware and have a lot of confidence that it's correct. We also have to have some way of dealing with shared state. Right, if we're sending the same request to these two variants and they're both sharing a database, well, they can't both send the same update to the database. So we either need some way of replicating the state as well, which gets pretty expensive, or we need some way of dealing with shared state. The other questions this poses, how do we actually get the security properties we want? We'd like some way of proving that we have two variants that are disjoint against some class of attack. This is more complicated than it sounds. One of the things we have to think about is multi-stage attacks. You could have a sequence of requests where no request by itself crashes one of the variants, but they get them in different states. And then a request that actually executes an attack successfully on one of the variants without crashing the other one. With the simple property that I described of splitting the instruction set, that's probably not feasible. With some of the other ideas like changing memory, that probably is. So we have to be very careful about the assumptions when we try to prove that the variants are really disjoint. The other thing we have to think about is, can we get higher level properties? Right? So all the examples I've talked about so far have assumed that the attacker needs to know addresses in the code or needs to inject instructions that run directly on the processor. And we seem to have pretty good ways of dealing with that. But lots of attacks don't rely on that assumption, that they can attack an application based on the higher level semantics of the application. And so we need to try to think of ways of making that kind of property disjoint. And so that brings me to the real jaws of the talk, which is when we try to understand how much security diversity is giving us, we have to think about the perspective of the attacker. So from the perspective of a parasite, all humans are very different. Right? From an influenza virus perspective, the diversity in human immune systems is good enough that one virus can attack all humans. From the perspective of a great white shark, well, humans are all really similar. They're all slow, they're all bad swimmers, and they're all really tasty. So if we want to get diversity that works against attacks that are more like the great white shark than the parasite, we need to think of ways of getting diversity in the way we run processes that is at a higher level than just at the instruction set or the memory addressing. So to summarize, diversity defenses have a lot of promise. They easily defeat all existing attacks that aren't designed to get around them. But a determined adversary may be able to get around them. And certainly, we've seen the examples today where ISR only protects the server for about 6 minutes against a determined adversary if certain conditions are true. But I think there is good promise here of doing things in security where we can actually prove properties. And the problem of protecting a secret won't be part of what we need to get security. So these are the students who did the work. Nora is a first-year grad student who did all the work on breaking the randomization keys. And Nate is about an N-2-year grad student who did the micro VM code. So any questions?
I would say the ISR will be, well, as can avoid lots of code injection attacks, but may not be effective to the return to libc attacks. So just
right. So the return to libc attack doesn't require the attacker to inject their own code. It's using code that's already there, so it's already encrypted in the right way. If you can accomplish your goals with a return to libc attack, ISR won't help. Yes.
So this new architecture with the replicated servers, I mean, is it doubling the effort needed on the part? I mean, so it's preventing certain kinds of attacks.
Mm-hmm.
But more generally, is it doubling the effort that's needed, or is it making it at best doubling?
It could be more than doubling the effort, right? It depends on how you implement it. But at least the most secure way of implementing it would be to have completely separate boxes that implement the two variants. So there's no threat of them not being isolated. And that may sound expensive. Buying twice as many machines, using twice as much power, certainly is expensive. I think if we go back to the analogy of what biology does to ensure diversity, it's probably a lot less expensive than what biology does. It may be expensive compared to other proposed ways of getting computers to be more secure. But it has a property that I think is desirable enough that maybe that cost is worthwhile. The other possibility is that maybe you can implement it on one machine, having separate processes, so the costs are not that high. We'd have to be a lot more careful to make sure that they're isolated enough. And so we're giving up a lot of processing power. We're running effectively twice as much. But processing power is effectively free now, so maybe that doesn't matter.
But let's say we are able to achieve this, let me call it complete isolation.
Mm-hmm.
Then what is the claim? Is it doubling the effort, or is it making it impossible to?
It's more than doubling because, right, you need both servers as well as the input replicator and the monitor. So it certainly does increase your costs quite a bit.
Well, actually, I think there's a better attack schemes. Suppose the attacker have been aware of a machine which is not protected by the ISR. So you can just compare the content. Suppose after several bytes, I can read a random memory address. Just compare the content and pick the key.
Right. So if the attacker can read the code, if the attacker knows the ISR encrypted code, then they can easily determine the key if it's an XOR key. The assumption here is that it's a remote attacker who can't do that.
But it's sometimes very easy for attacker have machines which do not protect by the ISR.
Right. Certainly, it's something. If you're relying on keeping that secret for your defense, it's something you need to worry about. The nice thing about the secretless security structure is that it doesn't have that property. Right. The attacker can know absolutely everything about both variants. It doesn't provide the attacker with any useful information for doing the attack.
Any other questions? Thank you, David.
Okay.